Okay, Jai Hind to all. Today I'm here to present the video lecture on subject signals and system, and code is BEC 403, and I'm Dr. Amit, Associate Professor in EC Department of Akgec GEC. The topic that I have chosen for my first lecture of this series is signals and systems. In this particular video lecture, I'll discuss about the introduction to signals and systems. Means what do you mean by a signal, what do you mean by a system, and along with the classifications of signals and systems, that how you will classify the signals, how you will classify the systems, and we will also see some of the numerical problems based on it. Okay, so let us start. Introduction to signals. So signal is basically anything which carries some information. Okay, so we are seeing these signals from the ancient times also, wherever people are used to use signals for the purpose of communication from one place to another. And but here in this particular subject, we will study the signals which can be represented mathematically. Only then we can do some mathematical analysis over it. Okay. So signal may also be, if you'll see the definitions, so signals may also be defined as any physical quantity or variable. It is any physical quantity or variable which is basically varying with time, space, temperature, pressure, distance, or any other independent variable. Means signal is basically you can say a pattern which is drawing between independent variable, that may be time, space, pressure, anything, and along with the corresponding y information, like in corresponding to time we will see the amplitude. Okay, so if we are having some pattern between these independent variables and dependent variables, then we can represent it as a signal. Okay, so we can see here that signal information is contained in a pattern of variations of some form. So this type of pattern we are getting. Dimension of a signal is defined as the number of independent variables used in a signal. Means if we'll describe the signals like one-dimensional signal, two-dimensional signal, three-dimensional signals. So signals dimension means the number of independent variable on which the output of the system, output of the signal depends. Like if I am writing y equals to at, it means there is only one independent variable, time. So you can say this is an example of one-dimensional signal. Like let us suppose I am taking an example wherein y is output of a and b, two independent variables. So in this case we can say a and b are two independent variables. So this signal is a two-dimensional signal. Okay. Now if you'll see the example, in RC circuit, the pattern of variation over time in the source and capacitor voltage are examples of signal. Like let us suppose we are having a source voltage Vs, and we are having you can say resistance and capacitor like this. Okay, voltage across capacitor is Vc. So let us suppose we are having source voltage Vs, resistance we have put it over here, then this is voltage is Vc, and this is resistance R. So now as long as time passes, so with the respect of time, what happened, the voltage across this capacitor changes, and also the source voltage changes. So we will draw the pattern of source voltage with respect to time and the voltage across the capacitor with respect to time. Then the variation or the pattern that we are obtained basically is the signal. Okay. So example of signals that we encounter in our daily life are basically speech, music, picture, and video signals. Like we'll see speech and music, these are examples of one-dimensional signal. Picture is an example of two-dimensional signal, and video is an example of three-dimensional signal. Okay. Now signal classification. If we'll classify the signal broadly, then we can classify it as like continuous time signals and discrete time signals. So a continuous time signal which is defined as a signal which is defined at each and every instant of time. Means if here is t and here is basically the amplitude, then continuous time signal is somewhat which is for which we are getting value of amplitude at each and every instant of time. Okay. So continuous time signal represented as xt. So this signal is xt. Is defined for a continuum of values of the independent continuous variable time t. So here t is the continuous variable, and here if you represent xt, then this xt can be represented either by a function or a graph somewhat like this, or maybe function like xt equals to you can say 2t square plus 3t plus 5 like this. Like in this case, these are the examples of continuous time signals. A discrete time signal is a signal which is defined only at discrete time instants. Okay, the amplitude of the discrete time signal between two time instants is not defined. Okay, so it is defined as like continuous time signals are defined as xt. These signals are defined as xn. Like, but here in this case, time t can be any value. Because it is continuous, but here n will take only discrete values. Okay, n will take only discrete values. So if we'll draw xn, then xn may be xn is basically discrete, which is defined out at only discrete time instants like this, which is like 0, 1, 2, 3, 4. So here we can see the value of xn is only defined at time at value of n 0, 1, 2, 3, 4 up to so on, and between 0 and 1 or between 1 and 2 and between 2 and 3 this value is not defined actually. So now xn can be defined by various, or you can say discrete time signal can be defined in various manners, like it can be represented like graphical manner, functional, tabular, sequence representation. So these are various ways by which we can represent the sequence xn. The most useful way of representation of discrete time signal is sequence representation, wherein we are writing, like if I write this signal in form of sequence representation, and these magnitude are, let's say 1, this magnitude is, let's say 2, 1, 2, 1, 2. So you can write it like 2, 1, 2, 1, 2, and we'll put arrow like this. So this arrow value will represent n equals to 0. Okay, so example of discrete time signal is weekly stock market index is an example of discrete time signal, and for continuous time signal example is speech signal. Okay, now another thing is continuous and discrete amplitude signals. So continuous time signal can take values in the continuous interval xy, where x may be minus infinity and y may be plus infinity. So then xt is called an continuous time continuous value signal or analog signal. And if discrete time signal can take only a finite number of distinct values, then we call this signal as a discrete time signal. Okay, so if we'll see from here, we will find this is continuous time continuous amplitude signal. We can see the amplitude is continuously varying with respect to time. So you can say this signal is analog signal when continuous time continuous amplitude signal. And here we can see discrete time. We are having discrete time, and values at these discrete times are also discrete. So we can call it as digital signal. Here we can see time is discrete, but these values which we are getting at these time instants are not basically countable values. These are infinite values, because you can see there are no values assigning to these. So these values are in a range. So that's why we can say this is discrete time continuous amplitude signal. Another type of signal is also continuous time discrete amplitude signal. Here we can see this signal is continuous in time, but you can see only finite number of counted values are represented. So that's why this signal is continuous time discrete amplitude signal. Okay, now we will see the classification. We have seen the broader classification. Now each of the continuous and discrete time signals are classified in these manners. So first one is deterministic and non-deterministic signals. So if we'll see talk about deterministic signals, so these signals are completely specified in time. Like if we can write an expression for this, like 5t square plus 3t plus 2. If we are able to write this type of expression, so then these type of signals are deterministic signal, because at a particular time you can find out the value of signal, because these signals are defined completely in time. Okay, and example xt equals to 80, xt equals to 5t square plus 3t plus 2 like this. Okay, the signals which are not deterministic are called non-deterministic, and it is also called random signals. And the example of random signal is basically the you can say the noise signal. Noise signal is an best example of the a random signal. So in case of random signal, we cannot basically exactly obtain the signal at a particular time instant, but we can predict the value of the signal at a particular time instant based on some probabilistic aspect. Means getting the value of a signal equal to something is given on some probabilistic aspect. Okay. Then second type of signal is periodic and aperiodic signals. So periodic signals are defined as signals which repeat itself after a certain time intervals, like xt plus t equals to xt, or xn plus n naught equals to xn. So this is for continuous time signal, and this is for discrete time signals. And the smallest value of t or n naught is known as fundamental period. So the minimum value by which a signal is getting repeated itself is the fundamental period. Okay. Next is even and odd signal. So even signals are signals having even symmetry, or you can say symmetry about vertical axis. Okay. Like and these type of signals are defined as, for continuous time, xt equals to x of minus t and xn equals to x of minus n. If you will see our sinc function, this is a sinc function. If you will see this sinc function, this function is symmetric about vertical axis. Xt equals to sinc of t. So this signal is symmetric about vertical axis, and this signal is an even signal. Okay. Or you can say example is cos signal and sinc function. Here the example is sine signal. Sorry, this is also a even signal and odd signal. Here example is sine. Like for a continuous time signal, odd signal is defined as xt equals to minus of x of minus t, and for a discrete time signal, xn equals to minus of x of minus n. Okay. Then even and odd component we can also find. Even component can be found using the expression. First of all, we will have the signal xt given, so we have to find out the even signal and odd signal, even component of signal and odd components of signal. So this is obtained by using this formula, half of xt plus x of minus t, or x odd is a half of xt minus x of minus t. So based on this, we can find out the component, even and odd component of a given signal. Then signals are also classified as causal, anti-causal and non-causal signals. So causal signals are signals which are defined only for t greater than 0. These signals are defined for t greater than 0, and for t less than 0, these signals are 0. So this is basically a unit step signal which is defined only for t greater than 0, and this is basically a causal signal. Okay. Now, if we will take its mirror image, means if we are having a signal like this, which is only defined at t less than 0. Okay. Here for t less than 0, the value is 0, and here t less than 0, the value is this. Here t greater than 0, the value is 0. Okay. So this is u of minus t. Okay. So this signal is anti-causal signal. Okay. Anti-causal signal. Okay. So signals are defined like causal signal, anti-causal signal, and also if a signal which is neither causal nor anti-causal is called non-causal signal. Means the signal will start, let's say, for before t equals to 0, and also everlasting after t equals to 0, like this type of signal. If we are having this type of signal, so you can say this is non-causal signal. Okay. Non-causal signal. Okay. So this is about causal, anti-causal and non-causal signals. Now, if we'll see the energy and power of a signal, energy of a continuous time and discrete time signals can be obtained using these formulas, Ex and Ex. This is for continuous time signal, and this is discrete time signals. And power of continuous time signal, discrete time signals is defined using these expressions. So with the help of these expressions, we can find out the energy and power of a given continuous time signal or a discrete time signal. Okay. Now, if we'll see, energy signals are also like, energy signals are signals having finite energy and average power is 0, and power signal are having infinite energy and finite power. Okay. Now come to the systems. A system is defined as an entity that act on an input signal and transform it into an output signal. Like here, if we are having an input signal xt and we want this output signal yt, then we'll pass it through a system. Okay. The response or output of the system depends upon the transfer function of the system. Okay. So like if we'll represent it in frequency domain, let's say this is xs, this is ys, and this will become hs. So ys will become xs into hs. Okay. So this is about the system. Systems can also be broadly classified as continuous systems and discrete time systems. So continuous time system is one in which the variable that we are using is continuous time input signal. So here continuous time input signals are transformed to continuous time output signals. So this is the way by which we can represent it. Here xt is the input and yt is the output. And for discrete time signal, these are defined as xn and yn. Okay. So now first of all, we will classify continuous and discrete time systems both as your linear and non-linear systems. So linear systems are the systems which follows the principle of superposition. Superposition simply implies that the response resulting from several input signals can be computed as the sum of responses resulting from each input signal acting alone. Okay, so if we'll describe this linear and non-linear systems, so if this system is following the principle of superposition, then it will follow these two properties. First one is this and second one is this. First property is called as additivity property and second property is called scaling or homogeneity property. So for a signal, for a system to represent linearity, it must show the principle of superposition, must follow the principle of superposition. Okay. Second is time varying and time variant systems. A system is time invariant if the behavior and characteristics of systems are fixed over time. Or other words, a system is said to be time invariant if time shift in the input signal causes an identical time shift in the output signal. So it means what we are doing, let's say there is a signal xt corresponding to which we are getting output yt, and if we are providing any shift, let's say t naught amount of shift to this, so this, if providing this in t naught amount of shift, if the output is also shifted by amount t naught, then we can say system is time invariant. Otherwise the system is time variant. So this is also applicable for discrete time systems. Here the shifted amount is n naught, let's say, and input is xn. Then we will see causal and non-causal systems, like we have seen anti-causal signals, causal signals and non-causal signals. Here we see causal and non-causal signals. So a system is causal or non-anticipatory if the output at any time depends only on the value of the input at the present time and in the past time. Okay, but not on future values of input. So causal systems are the systems wherein the present output of the system depends upon the past values of input as well as present values of inputs, but not on future values of system. Means like if your system is, let's say, fx, then this, sorry, ft, then you can say it will be dependent upon the values, let's say, in present values of input. Okay, present values of input, past values of input, like this, but there will be no future value of input. So this is causal systems. And in case of non-causal systems, if the present output of this system depends upon, if the present output of the system depends upon if the present output of the system depends upon past input values, present input values as well as future input values, the system is non-causal systems. Now we'll see all memoryless systems are causal systems since the output responds only to the current value of the input, but not all causal systems are memoryless systems. So we'll see the memoryless systems, then we'll see it. Stable and unstable system. A stable system is one in which input leads to response that do not diverge. A system is said to be bounded input, bounded out stable if and only if every bounded input results in a bounded output. Okay, so let's say our bounded input is mod of xt and corresponding the value of it is bx, which is a finite quantity. Then if applying this bx, if we are also getting our output yt, which is less than infinity, then we can say system is stable, otherwise it is unstable. Now systems with and without memory. So with memory systems are systems having memories in it, that are also called dynamic systems. Systems which are not having any memory are called static systems. Means if we are applying input, present input, and we are getting the present output, means system there is no memory to store it. So example of static systems are, or memoryless systems are, register R with input xt, so that we can get the output yt. This is an example of static system or memoryless system. Now, if we are introducing along with the register, we are introducing capacitor and inductor, then in that case our system will become a system with memory or dynamic system. Now, invertibility and inverse systems. A system is invertible if by observing the output we can determine its input. That is, we can construct an inverse system that when cascaded with the given system yields an output equal to the original input of the given system. So this is the invertible and non-inverse system. We are applying input xt to the system to get the output yt, and again if there an inverse system exists, then we get the value zt, which is equal to xt. So this, for invertibility, it is a must that the relationship between the input and output should be 1-to-1. Only then then an inverse system exists by which we will again get the output xt. Okay. This is about the classification of systems. Now we will see the problems like periodicity. So we have to find out the period, whether the given signal is periodic or not, and if it is periodic, find the fundamental period. Okay, so is compare it with xt equals to a cos omega 1t plus 1 minus sine omega 2t minus 1. So this is basically omega 1 and this is basically omega 2. So omega 1 equals to 10. Okay, so T1 is 2 pi by omega 1. Here T2 equals to 2 pi by omega 2. So 2 pi by 10 and here 2 pi by 4. So this signal is periodic if the ratio of T1 by T2 is rational. So here if you will see 2 pi by 10 into we will see it is pi by 2. Okay. So this is, if you will see, this is 4 by 10. This is, if you will see, this is 4 by 10. Okay, or 2 by 5. So from now we have to find out the fundamental period. So fundamental period is nothing but 5 T1 equals to 2 times T2, and this is equal to T naught, which is the fundamental period. So if we'll calculate the fundamental period, then it is pi. Okay, pi by 2 into 2 or 5 into this. So fundamental period is pi second. Okay, now this is for discrete time signals. Here this signal, you can see here, this is, let's say, n1, this is, let's say, n2, and this is n2, n3. So compare it with e to the power j omega naught n. Okay, so n1 equals to 1. This is a constant signal, DC signal. Okay, so which period is basically 1. So n1 equals to 1, and if you will calculate n2, so omega naught is, yeah, omega 1 equals to 4 pi by 7, and here if you will calculate omega 2 equals to 2 pi by 5. Okay, because this signal is periodic, because this signal is you can say DC signal, so it will not affect on the periodicity. Although we can take this signal also for finding out the periodicity, but we will not take it. So we will calculate the periodicity based on these two signals. Okay, so so basically n2 equals to 2 pi by omega 2 into m2, n3 equals to 2 pi by omega 3 into m3. So n2 equals to 2 pi upon 4 pi into 7 into m2. Now we have to choose the value of m2 so that this will become an integer value. So let's say m2 equals to 2. So m2 equals to 2 if you will choose, then n2 equals to 7. Okay, and here n3 will become 2 pi upon 2 pi into 5 into m3. So now you can choose the value of M3 as 1. So N3 equals to 5. So these signals are periodic if N2 by N3 is rational, which is actually rational. So now fundamental period is N0 equals to 5N2 equals to 7N3, and the value of N2 is 7, so this is equals to 35. So in this case the fundamental period is 35. Okay, so this is the another question. Here the signal is cos A cos B. So this is in the form of multiplication. So we can only apply the signal when the signal can be represented in form of addition or subtraction. So we have to first apply the formula 2 cos A cos B. So when we apply this formula, we are having these two signals. Now you can apply, you can solve this question on by own like the previous methods. Like this is omega 1 equals to 3 pi by 4 and omega 2 equals to pi by 4. So you can easily solve this. So here are the references of this video lecture. So you can easily go through it.